So if you think of the grid as, something that takes power in and puts the power out, it needs quite a lot of management to keep that whole thing running and stable. And then there's the steady state, but then there's disturbances. What happens if there's a fault, a disturbance, an event, a trip, and it's got to ride through all that and carry on doing its function. It's that kind of keeping that grid stable and operational that is the key challenge. When we talk about grid stability, it's the last thing you want is that kind of domino effect where one thing falls over and knocks another over and the whole thing unzips or falls over. So
what is a stability pathfinder?
Pathfinders will say, well, let's try out some way of procuring it and see how it worked, and then when we've done that a couple of times, we'll then morph into a more normal market. But we don't want to jump into a market because we're not really ready that. So it's about sort of priming and testing and creating a market mechanism to bring on a new kind of product or service.
Hello and welcome back to Transmission. Grid stability becomes increasingly complex with the growing integration of renewable energy sources. Enter technologies like synchronous compensators, advanced spinning machines that deliver the critical inertia required to balance the grid and ensure reliable power supply. In today's episode, Guy Nicholson, Head of Grid Integration UK at Statkraft, joins Ed Porter to explore the topics of grid stability, synchronous compensators, the stability pathfinders, and much more. If you're enjoying the podcast, please hit subscribe so you never miss an episode, and give us a rating wherever you listen. Let's jump in.
Hello and welcome to another episode of Transmission. Today we are joined by Guy Nicholson. Guy, welcome.
Thank you, Ed.
And today we are going to be running through the world of synchronous compensators.
Yeah, so I believe.
Very exciting. Okay, so we've been wanting to do this for ages, this world of sync comps, synchronous condensers, synchronous compensators. What does it all mean? How do they all work? I'm super excited to get into it. But first, maybe let's start off with a little bit on Statkraft. Who are Statkraft and what is your role within Statkraft?
Yeah, so Statkraft's state-owned by the Norwegian government. We are the largest renewable generator in Europe, thanks largely to our Norwegian hydro assets. And we're developing wind and solar and battery and storage grid services stuff around Europe and to a degree around the different places around the world. So it's kind of quite an exciting time to be in the company in this kind of expansionist mode. Yeah.
And your role within Statkraft?
Yeah, so my role is Head of Zero Carbon Grid Solutions. That's my title. And I'm developing and I've been developing what we call our greener grid parks, which are sites where we can deliver services to the grid. So it's about decarbonising the grid and helping renewables run the grid. So I guess my whole career has been based in renewables, connecting renewables to grids. And it's now nice to have got to a stage where there is so much renewables on the grid that sometimes, particularly in COVID, in lockdown, when we had low demand on the grid, high renewables, the system operator had to turn off a lot of renewables, turn on a lot of gas, because we couldn't keep the grid stable without doing that. And so that was a kind of wake-up call for everybody. This was like leaping the clock forward 10 years. And so lots of lessons learned from that, and I think very exciting about what's coming. So that was a glimpse into the future, I think.
Yeah. And to get into that role, do you kind of have a technical background, a commercial or a regulatory background? How do you find yourself there?
Yeah, so I've worked in renewables all my life. I started grid connecting stuff in the early 1990. A lot of that was landfill gas at the time, wind, mostly distributed, and then that progressed to transmission connected to offshore wind, and then solar came along. Primarily, I worked for developers, manufacturers, but primarily as a consultant and primarily supporting developers to get their grid connections done. So never liked anything more than a grid company saying no, it can't be done, because then I was determined to try and find a way of doing it. And yeah, built a company called eConnect, which sadly went under, but was a great leader at the time in this. And was involved with the largest wind farm in Europe, P&L in Wales in the early 90s, first wind farm in Scotland at Hagshaw Hill. I was the expert witness for the Cleve Hill substation for London Array, connecting into the grid there. And so lots of things along the way, all about getting renewables connected.
London Array being a large offshore wind site.
So that was where it came to shore in Kent at Cleve Hill. So the substation's now built, and for a lot of years, but
Cleve Hill also the home of, I think, a very large solar and battery storage project.
Yeah, and now that's kind of piggybacked onto that solution. Yeah.
And we talked a little bit about their sort of a grid operator saying, "Oh, this can't be done," and when they talk about that, like, why would they say that?
Well, it's interesting because one of the things that I did before I started Grid Connections stuff was a lot of kind of off-grid standalone projects, including power systems for Mongolian nomads, lighthouse stuff. But I spent a year on the island of Fula off Shetland putting in a grid system there because they didn't have any power grid, and running it on wind primarily with a small amount of hydro, some diesel backup. And so that taught me, and that was without any batteries in those days or any inverter technology. It was all fairly conventional rotating machines. And so that taught me a lot about how to run a grid system on a small scale. And then when I came to grid connecting renewables, and you got transmission system operators, like EirGrid saying, "Oh, we can't have more than 5% economically and 10% technically." I'm going, well, hang on a minute. If a rookie engineer like me can build and operate a system on a small island, which is quite challenging, why can't lots of clever engineers with all this grid experience do it on a big grid? And that has kind of always been a fallback. Yes, it can be done. It's just about up here. It's about the mindset of doing it and finding solutions.
What are the pinch points? So as you start to kind of become a more renewables dominated grid, like what are the parts of kind of what are the grid specifics that start to get more difficult?
One model of the grid that people use for kind of frequency and inertia is this kind of bathtub, don't they? You have water pouring in through various taps. That's your generators, your in-feeds, and you have lots of plugs and pipes going out. That's your load. And then, if you take more out, the water goes down. You put more in, the level goes up. That's a kind of one model. But what it doesn't perhaps model very well, a number of things it doesn't do very well, but it's a good analogy. But so if you think of the grid as, something that takes power in and puts the power out, takes power in from generators and in feeds, interconnectors, whatever, out to consumers, to users, it's not just like a bath. It needs quite a lot of management to keep that whole thing running and stable. And then there's the steady state, but then there's disturbances. What happens if there's a fault, a disturbance, an event, a trip? And it's got to ride through all that and carry on doing its function. It's that kind of keeping that grid stable and operational that is the key challenge. And renewables are primarily inverter-based. Inverter-based resources is what the North Americans like to call it. I quite like that term. So, and also along with wind and solar, they're like that. Batteries are also inverter connected, and so are interconnectors. So as we move to a system where we've really dominated by wind, solar, batteries and interconnectors as the main, players on the grid, pushing out the nuclear, the carbon capture, the gas and everything else, then you don't have the old synchronous machines that you had with coal, gas, nuclear, hydro. So pushing those synchronous machines off the system.
And what did those synchronous machines provide?
So that's when we come to our favorite term like inertia, system strength. I'm going to talk about fault current, reactive power voltage control. So, and I know you probably want to tease into each of those, so I don't want to jump the gun, but I think inertia is probably the easiest one to grasp. So those spinning machines, rotating machines have got spinning mass and so on. So turning round and going back to my bathtub analogy, if you have a mismatch between generation and demand in feed and X feed, that mismatch comes from inertia, comes from the kinetic energy in inertia. So, if we have a trip on the grid, and we have about 3 large trips every fortnight, and we loss or of load or demand, frequency step and that. So when you have that sudden disconnect, that mismatch in energy is taken from the rotating inertia in the grid. So the spinning machines slow down slightly to provide, and the energy comes out of them as they slow down and meets the gap, fills that gap. So the thing about that inertia is when you get a trip like that, it kind of slows the rate of change of frequency down. So if you have a system with a lot of inertia and you have a trip, supposing, the North Sea Link trips to Norway, so we lose 1.5 gigawatts into the GB grid, then the frequency is going to start to fall until our friends with batteries all respond and, kind of pull the frequency back up. But it's that initial rate of change. So if you've got a high inertia system, it's going to change very slowly. And then everybody's got time to react. Batteries have got time to detect it and feed power in. The control room's got time to notice it and go, oh, we might need to schedule some more power. We might need to call someone up and get them to put more power into the grid. So that inertia gives you time to react. If you have a low inertia, that frequency falls very quickly. And the risk is, before anything's got time to react, your frequency has fallen and you've got some sort of partial blackout or worst scale, full blackout. So yeah, that's the kind of thing.
And I think that's kind of a really important thing to talk through. So if your frequency moves too fast and hits one of the limits, what happens to a grid? How does that actually turn into like a partial blackout?
Well, let's take the last one, 9th of August 2019 in GB, and we had the last partial blackout. And what we had was a combination of Hornsea offshore wind farm tripping because of a transmission thing, and I can talk more about that perhaps later on. We had combined that with a CCGT tripping. So you had 2 trips, you had disturbances on the system that then tripped other generations. So I think we lost about 1.7 gigawatts or something like that. And so the frequency, there was a few steps, but the frequency ultimately fell to 48.8 hertz. And that's the level where you disconnect some load. So the load disconnection that's distributed around the grid is there to protect the grid from that complete blackout. So you hope that, the frequency comes down, you trip some load and it bounces back again. So that's the defense mechanism, but the result is some consumers do get interrupted. And particularly that event happened on a Friday night during rush hour. Because the frequency dropped below 49 hertz, some of the trains that were from Germany had some software in them that said, if the frequency is below 49 hertz, something disastrous has gone wrong, because the European grid never goes that low. Yeah. So lock out, call for a technician. So all these trains all locked out and the drivers couldn't restart them. And so people were stuck on trains.
I was stuck on one of those
trains.
You were? Yeah, I was stuck on one of them. I can confirm this happened, yeah. Okay, no, brilliant. I think that really helps people to kind of picture both the move to more inverter-based resources, the spinning systems we have, and then also what kind of happens when it goes wrong. I think just for people who are maybe not so familiar with the energy space, one thing that might come up is someone will say, well, look, you're after spinning things. I've seen a wind turbine, they spin. Why doesn't that help?
Excellent. Yes, great question. So, and wind turbines, did used to be directly coupled to the grid usually with induction generators. Now they've been decoupled with inverter. So the spinning part of the wind turbine, the rotor, the generator, the gearbox are not linked to the grid frequency. So unlike one of our synchronous compensators or unlike a gas or coal station where the grid frequency and the machine are locked together through that synchronous coupling. That's not the case even with wind, with spinning. And interestingly, there was a kind of fad at one stage for wind inertia or synthetic inertia from wind. It wasn't really inertia, it was frequency response, So the idea was, well, we've got these spinning rotors. If we're kind of need power in the grid, what we can do is use our inverters to slow those rotors down, pull out the energy and feed it into the grid. I think that was a great idea. But, if you imagine you've got a grid with, say, 30 gigawatts of wind going and you lose the interconnector, 1.5 gigawatts to Norway, then you take your wind and go, right, okay, we've lost 1.5 gigawatts. Let's slow down our wind turbines, pull out, instead of 30 gigawatts, let's pull out 31.5 extra energy. You solve that problem for a short time. But what you've done then is you've slowed all those wind turbine rotors down and you've disturbed the optimum level of their wind capture. So now your 30 gigawatt wind farm fleet turns into a 25 gigawatt wind farm fleet. So you've solved a 1.5 gigawatt hole for 30 seconds and you've created a 5 gigawatt hole a minute or 30 seconds later. So unless you were relying on lots of OCGs to start up or fast diesels or something, it hasn't solved any problems.
OCGs, open cycle gas turbines.
Thank you. I knew we'd be into accidental acronyms, so well spotted. Thank you.
Okay, and maybe just like last one, and just to kind of defining what's going on here. So we've talked a little bit about frequency response. So things like batteries sensing that frequencies moved and then responding to it.
Yeah.
And we've talked about inertia.
Yeah.
What is what is the time period we're looking at here between the kind of the gap between the real kind of live system and then the first response from, say, a battery?
So the great thing about this synchronous machine with a synchronous compensator or generator or motor and the inertial response is it's built into the physics, it's locked in. So that machine is rotating with the grid. If that's 50 hertz, it's rotating round at maybe 1500 RPM. And if the grid slows down, it's dragging that machine. That machine can't, unless it pole slips in a stability issue, but in a frequency response, that's not going to happen. So it's locked together with the grid, and that's so if the grid frequency slows, it's pulling energy out of that drivetrain, that machine, that spinning mass. Okay. If the frequency increases, it's having to push energy into it to speed it up. So it's built into the physics. So that's the inertial response, and that's so really important for that kind of when you have an instant loss of a large infeed like a big interconnector or a big generator. That's so important to rate of change of frequency. The batteries and batteries have done a fantastic job in terms of frequency response. So when enhanced frequency response came in, I remember I was involved with Element Power at the time, sitting around the board table going, what price we're going to put in, and the price was mooted. And I went, no, it's worth 3 times more than that. We can't bid that low, because it really did cut the price of frequency response in about a third. And since then, as you know, that whole frequency response cost has even come down. So, batteries have really massively reduced cost of frequency response on GB grid by probably down to 10% of what it was 5-10 years ago.
That's more or less the right number, which is this kind of crazy win for consumers, right?
Yeah.
In that instead of paying large gas turbines to be running for frequency response, we're getting the same thing, but at low carbon and also for like a tenth of the price. Like it's a huge win of transitioning your system. So, okay, well, let's then go from kind of what is grid stability, why is it important? Let's go into the stability pathfinders.
Yeah.
So what is a stability pathfinder?
So the Pathfinders was something that Grid brought out in terms of, and they've used it for a number of things. Stability is the most notable to say, well, we want to explore how to create a market for this. And, hands up for the ESO, the NESO, and the history have had a track record of going out and procuring stuff rather than just mandating it, and that is to be applauded. So the Pathfinders will say, well, let's try out some way of procuring it and see how it worked, and then when we've done that, a couple of times we'll then morph into a more normal market, but we don't want to jump into a market because we're not really ready that. So it's about sort of priming and testing and creating a market mechanism to bring on a new kind of product or service. Yeah.
And so what does that look like in terms of the projects that you're working on?
So interestingly, so go back to Stability Pathfinder Phase 1. That was announced on the 5th of November 2019, coincidentally not long after the 9th of August event. So there's some linkage there of, oops, we might be short of inertia and stuff. And was a very fast turnaround. You know, we bid in January. So November to January. It was designed really for existing generators who could operate in sync comp mode. So, you know, maybe put a clutch in between the generator and the prime mover, or close down the power station and just run with the generator as a synchronous compensator, synchronous machine.
What was it buying?
It was buying inertia, but not totally actually, because when you analyze the bid prices, and it's there in the public domain, you can see that Statkraft's products were the highest paid for just inertia, if you like. Some products at a higher price than us didn't win a contract, but there were a couple of projects, Kruchen and Rassau, that won contracts at much higher prices. So if they were just contracting inertia, they wouldn't have been in merit order. So they were contracting inertia and what else? Short circuit current, system strength, voltage control, reactive power. But it wasn't explicit, so it was a bit opaque, but given the timescales, maybe fair dues.
And it's maybe, just going back to that frequency response example, it's kind of a good demonstration of run a Pathfinder, see who can respond, get yourself the right terms of the market, and then run it into a kind of an auction type process going forward. And if we take the example of the frequency response we've just been talking about, if you'd signed those gas units up to a 10-year contract from 10 years ago, we'd all be locked into some really expensive contracts. And the hope is that as we build a market, better solutions will come along. Okay, so one of the interesting things about this is that not everyone's doing this, right? So why are these markets attractive to Statkraft?
Well, I think we, again, going back to pre Statkraft Element Power, because Statkraft bought Element Power, we had a synchronous machine running on a wind farm in Ireland for various reasons, to kind of explore this concept of how do you make wind and the grid work better together. And so then we realized that, what we're going to need is a lot of inertia on the grid. When we've got a lot of wind on, we're going to push off the gas. There's going to be no inertia. We're going to need inertia, at least, on the grid. So we were exploring high inertia synchronous machines, synchronous compensators to do that. And we thought it was going to happen in Ireland first. And National Grid ESO or NESO jumped the gun on AirGrid by quite a way. Actually, AirGrid have eventually caught up and done their low carbon inertia service tender. But so we were there. We were actually the reason we were able to do our new build projects at Keith and Lister, which won contracts in Stability Round 1, was that we were already working with GE on their rotating stabilizer for some of the projects. And so we were well down the road with procurement, design and everything. And when the SPP Stability Pathfinder Phase 1 tender came out, we were right, we've got all the ingredients here, we've got the machines. We had a couple of sites that we were developing for other reasons. We put all that lot together and were able to bid in, and because the timescales were very aggressive to actually get delivered for a new build. We could just do it.
Let's do that. So from day one of the Stability Pathfinder being awarded, how long does it take you to turn that into a project?
Yeah, you're talking 3 years kind of timescale or more, depending on, it's primarily your grid connection. And since then we've had the Ukraine war, we had the impacts of COVID, the whole supply chain thing, so now it's about lead time for transformers, switchgear, the machines themselves, everything. It's all primarily driven by lead times and getting a good connection. With the hiatus of the connection queue at the moment as well is just another spanner in the works of things. Yeah.
And do grid operators want a sync comp on their site? Is that something that they want that on their network, or is it kind of a trouble for them?
No, it's great. I mean, if we look at this, it's quite interesting to look at Stability Pathfinder Phase 1's, not just our projects, but everybody's. And, they were contracted primarily for inertia, but we're needed for inertia, maybe, I don't know, 30% of the time, something like that, or less. But we're actually they run us pretty well all the time. And even when we're not needed for inertia, and that's because, of the system strength capabilities that the synchronous machine brings, the fault current, the ability to deal with voltage fluctuations, supply reactive power, where we soak up harmonic currents through our machine windings. So there's all sorts of other benefits that the machine brings.
Yeah.
So we're not just put on the bars when there's low inertia. We run pretty well all the time because of that insurance policy. It's costing grid a little bit of money to supply for Stability Pathfinder Phase 1. They pay for the energy that the machines use. So, you're talking about about 2 megawatts for 1 gigawatt second of inertia. So if you had to, the grid needs, let's say, 100 gigawatt seconds of extra inertia. So that's going to be about 200 megawatts of power to run all those synchronous machines to provide all the inertia you need on the grid, and a lot more besides the inertia, that whole system strength of those machines running.
Can we stop there, because that's really interesting, right? So 200 megawatts of power will get us all of the inertia we need for the GB system.
Yeah.
Because when we talk about the transition, like, one of the things that's really kind of always comes up is kind of the lack of inertia on the system. And when you phrase it like that, it feels so doable.
It's very doable. Yeah, very doable. So interestingly, so I say, at the moment, the Frequency Risk Control Report, FRCR acronym, we're on about 120 gigawatt seconds of inertia, and they're talking about bringing that down to 100. I think that's a risk, and I would caution against rushing into it without some extra contracts of frequency response inertia. But I've lost my thread now.
But let me pick that up. So one thing we are seeing, so that inertia that's being required from the grid is dropping from like 120 to around 100.
It was 140. The previous FCR had dropped to 120 earlier this year. They're talking about dropping it again to 100 this year. It's quite a steep fall and it's a bit, it's not properly thought through in my mind.
But is part of the logic there that the growth of battery storage and the success of the frequency response from it, even though the inertia is falling, even if it does fall, you'll still have the batteries there to bring it back to 50 hertz.
You've got that fast frequency response. Yeah. So there's a bit of a combination, as I say, the inertia determines what the kind of rate of change of frequency is. So if you've got a faster response that batteries can give, we're talking about fast response in 300 milliseconds or that kind of time scale, compared to the old, gas turbines and pump storage, which needed 10 seconds or 1 second to do anything and 10 seconds to get there. It's much faster. So you can have higher rate of change of frequency. And we've moved to that now from, 0.125 hertz per second to 1 hertz per second. So they've already moved that. But it's it is risky to make all these changes given what's going on the grid. We
have to talk about that. So what are the risks? Why would you caution that grid moves slower on the drop in inertia?
There's a lot to unpack in that. The FRCR report, this thing is really came in for when we moved from this 0.125 hertz per second limit, which was driven by rock-off protection relays on distributed generation. So what we used to have, go back to the old faults like 9th of August, again, you have a fast rate of change of frequency that gets picked up by protection relays on lots of distributed small stuff and that all goes, oh, we think there's a local grid fault, so let's trip off. And so you start with a largish problem with a big trip on the grid, but that creates a disturbance on the grid, which then cascades that problem. It's that domino effect. When we talk about grid stability, it's the last thing you want is that kind of domino effect where one thing falls over and knocks another over, and the whole thing unzips or falls over. So trying to decouple things so that they're robust against something else going wrong is key about maintaining a stable grid.
So you're worried about the kind of systemic element, but I suppose the other side of it is also true that you wouldn't want, say, the UK to be procuring double the amount of inertia it currently is, because historically we've got that from gas, and that can be quite expensive, but also carbon emitting.
Yes. So, it's about getting the balance, and, it should be a cost benefit analysis. What's the risk of something going wrong? What's the cost of it going wrong? What's the cost of sorting it? And the cost of sorting it is going down rapidly. The cost of it going wrong is going up rapidly, because we're all so much reliant on electricity, and will be more so. And the risk in my mind is the backlash against, the whole decarbonisation of the grid and the whole net zero mission. If we have something that goes wrong and, we have a partial blackout or something like that, then critics will jump in and go, you're going too fast. You need to go back to fossil fuels. This is all a disaster. We've had that before, people blaming renewables for grid incidents and grid trips.
Whereas, as you're saying, this kind of 200 megawatts of power can get us all of the inertia we need.
Yeah.
Okay. And last question on the stability pathfinders. So they end. What happens when they end?
So, we've had stability phase 1, stability phase 2, which was in Scotland, stability phase 3. So they've procured 12.5 gigawatt seconds of inertia in 1, 7 gigawatt seconds in phase 2, and 17 gigawatt seconds in phase 3. Those phase 2 and phase 3 are still in construction and coming on the bars. All the phase 1s are operating. So that's, National Grid has now moved to a stability market, and we've just had the results of the first, what's called midterm round 1 auction or tender last week. So, that's showing that there's some new entrants in there. There's a couple of projects from stability phase 1 that have gone into that. Our projects will go into that annual market next year, along with a lot of others. So we're starting to see that annual market, so that contracts a year, and it's really for existing assets, but it's got some new build assets that are multifunctional in there. And there's also, alongside that, going to be a day ahead market. So let's say I bid into the year ahead with an existing asset, don't win a contract, then I'll drop into the day ahead market. That's still to be put in place. And theoretically, I could bid into the balancing mechanism, but would I actually get would I get skipped? Don't know. And then theoretically, there's what they call a Y-4 or long term. So if they need a lot more inertia than is kind of available with these year ahead contracts, then they can kind of do another stability pathfinder phase 4, but it won't be called that.
Okay.
But it'll be basically the similar model, really, if you like.
So hopefully people are getting a picture. There's kind of a really kind of robust process for bringing in new projects, but then also taking them through the course of their life into kind of serving the grid for the 20, 30, 40-year lifetime of these assets. Yeah,
great. And it's great for us because, when we got our board approval for building our stability phase 1, it was like a 6-year contract, and we were going to miss the first year of it, and we missed a bit more with COVID. So, with no prospect of what the market was at the end. So the fact that the ESO has, delivered on that market, has put it in place, that really creates a good, good vibes for investment in these kind of services and products.
So I feel like moving on from stability pathfinders, people are going to be at home kind of going, we've talked about synchronous condensers, synchronous compensators. There are so many terms for what seems to be the same thing. Like, what's the right term? Maybe first question, and then we'll come on to what it is second question. So like what's the right term for synchronous compensators?
Well, I'm going to turn your question the other way around just to be awkward. So yeah, it's a synchronous machine, and a synchronous machine can be a motor, can be a generator, or it can be a synchronous compensator. So if you take a synchronous machine and put a hydro plant on the end of it, spin it around, then it becomes a synchronous generator. If I put a pump on the end of it, it becomes a synchronous motor. If I don't put anything on the end of it and just connect it up to the grid, it's a synchronous compensator or condenser or rotating stabilizer, depending on what you want to call it. So they're all the same thing. They're all a synchronous machine. Depending on what they're doing, you can call them different things. And when they're a synchronous compensator or condenser or rotating stabilizer, it's just a different term for the same thing. Sorry for all the word soup there, but yeah.
No, I think it will help people because I've heard them referred to as many different things, and it's not always particularly clear what people actually mean by them. So it's useful clarity. But then, actually, what actually is that thing? Is it just like a giant spinning top?
No, so it's an electrical machine. So obviously they were built primarily as generators and motors in the first place, and then they have been used traditionally. I saw one at Tailem Bend in Australia, between Adelaide and Melbourne, where it's just doing voltage control. So it's a synchronous compensator, but just managing voltage. And then those sort of machines were replaced with power electronics, Statcoms, SVCs, switch caps and reactors. So those voltage control kind of uses kind of went away. And now we brought back synchronous machines for stability, inertia, and you can have machines. So like our G machines at Keith, they've got high inertia built into the electrical machine. So it's like a flywheel with an electrical machine wrapped around it, if you like. And then like our listed drive site, which has got ABB machines, they've got a standard electrical synchronous machine connected to a flywheel, and that gives it the extra inertia. And that's kind of a model that's common with many suppliers. So yeah.
And let's come back to the voltage control and Statcoms in a second, because I think we kind of just nudged that into the conversation, but it's kind of opening another can of worms. But I think just on to the synchronous condensers, just a sense of scale for people at home. Is it like the size of a bus? How big is this thing? Is it in a shed? Would you notice if you drove past it?
Probably not. So if I take our listed drive site in Liverpool, it's kind of tucked in between the cash and carry and the substation and a road, and it's a 1 acre site. On there, we've got a 275 kV transformer down to LV. We've got our medium voltage switchgear. We've got our cooling systems. We've got 2 sheds with the synchronous machines in. And the sheds are, in double-decker bus terms, probably about, 4 double-decker buses or something of that order. I've never actually tried to squeeze one in, but that kind of size.
Okay. And then within that shed, as you were saying, we kind of initially planned to run, say, maybe 30% of the time, but now more often running nearly all of the time. And so within there's essentially something that is spinning. Did you say 150 RPM?
So depends on the number of poles on the machine. So 1500 RPM is kind of probably the fastest. You might get 3000 RPM for a 2-pole machine. So I think I'm right. Listed drive's 1500, Keith's 500. So it's a 12-pole machine going slower. So depends on the electrical machine. But yeah, those kind of
essentially something in there spinning all of the time, and power going in to keep it spinning to pay for the frictional losses of the system.
Yeah, the windage, the friction, the bit of heating.
Does it generate a lot of heat?
So, let's say we're talking about for our machines round about 1 megawatt each. That'll vary depending on the reactive power and whether it's doing voltage control or not. So it might be less, might be more than that, and that energy goes into heat. So then that gets dissipated through the cooling systems. Yeah.
Okay. And how do they break and how do you maintain them?
Yeah. So, when you've got something high inertia like this, if you just disconnect it from grid, you might have to wait best part of a day for it to slow down and stop, unless you've got a break. Or, nowadays, we can slow them down. So you have to start them up. So you generally have some sort of variable speed drive, and that might be direct onto the machine, or it might be through a pony motor that spins it up and drives it up to synchronous speed, and then we synchronize it with the grid, close the breakers.
Okay, so you get it to 1500 RPM, close the breakers.
Get it in the right voltage, right phase, right orientation, close up, and then you synchronize the grid, and then you can disconnect your drive starter, and it's then brings in power from the grid to keep it spinning. And
so in terms of like I'm still stuck on this idea that someone's turned it off and then they've had to wait a day for it to slow down.
Well, that was a scenario. It's not the case.
Not anymore. Okay.
You need to pull the power out to slow it down somehow. Yeah.
And so what do you have to do to, like, how do you keep that working? Do you what does the maintenance program look like?
Pretty low maintenance. You've got to maintain the bearings. You've got to maintain the cooling system. I mean, the machine itself there's really nothing to maintain, go wrong, clean filters, these kind of things. So it's pretty low maintenance and manned sites. And very reliable stuff.
Okay.
Touch wood. Yeah.
Touch wood. Okay. And then, so sort of last question on this, who actually makes these? Because they feel like such a unique thing. You mentioned GE and ABB, right?
Yeah. All the usual suspects anyone who makes an electrical machine, synchronous machine, large synchronous machine. So anyone who makes a generator for a power station will make an electrical machine which can be used as a synchronous compensator. Yeah. So you pays your money, you takes your choice. Yeah, all sorts of varieties of flavors of size, speed, cost, inertia, fault level, reactive capabilities.
So there's a lot of flexibility in this in terms of what you can actually procure.
Yeah.
Okay. And then is GB sort of ahead of the curve on this, or are we kind of miles behind others?
No, we are really world leading in this, definitely. You think, so synchronous compensators have been procured by, in Europe, there's still a bit of despite the European directive that says these services should be let out to the market, there's still a bit of the TSO, well, these are our assets, we build these kind of things. So there's quite a few synchronous machines going in the Baltics because of, disconnecting from the Russian grid, the Soviet grid. There's Energinet in Denmark have got a couple of synchronous compensators sitting around some of their HVDC links. So not necessarily with high inertia, it might just be synchronous compensators delivering a bit of inertia and the system strength, voltage control things. So yeah, there's a bit of it about that. GB has led, particularly with the open procurement and competition. That's driven down prices. It's a highly competitive market. Talking about stability Pathfinders, it's kind of like waiting for the results. The worst thing is you haven't won anything. The next worst thing is you've won everything because you've obviously bid too low and you cocked up. So it's trying to make sure you win.
The right amount.
The right amount is key in this, really.
Definitely. Yeah. And that's the value of the Pathfinders, right? That you can start to put you start to get an idea of what the value is for the service, which means it's easier to procure going forward.
Exactly. And you start to discover the market price. You can look at everybody's bids. Yeah. The data's out there. So, you can kind of see how this all stacks up and and works out.
Okay. Yeah. And we kind of put a pin in a question earlier about Statcoms and voltage control. Let's go back to that. Why is a Statcom different to a synchronous compensator?
So a Statcom is like power electronics. So it's a bit like your inverter with instead of a battery, you might have a capacitor on the end of it. So you've got some energy storage, but not that much. So it's able to, particularly take in real power and move reactive power around. So
so it's not a big spinning mass, it's all kinetic mass. It's all done on power electronics.
Kind of the same as an inverter, for a battery system that's kind of can operate that in a similar manner.
Okay.
I'm not a power electronics expert, so some people on the podcast are going to go, no, he's off
Okay.
off the mark on that. So apologies to the power electronics gurus out there.
Yes, a call for our Statcom expert to come on and explain voltage control. And yes, please. I would be very happy to host them. Okay, so moving on to our sort of final two questions. So the first question is there anything you'd like to plug?
Yes, system strength. So I've used this term a bit liberally in this discussion, but and it wasn't really a term used much until a couple of years ago. It's starting to be used. It's not really defined. People want to know, well, what is system strength? And I think that the challenge as we move to inverter-based resources is we've got all of these inverters with their interconnectors, batteries, wind turbines, solar. They've all got software and programs and stuff behind them. And those control systems can interact with each other in bizarre ways. And it's impossible to predict whether that might happen. People try to create models, they try to analyze it, they try to, train them and test them, things like that. But you can never be absolutely certain. So the risk is we've got, these inverter-based resources becoming unstable in some way, or some of them, or one of them, it doesn't take much. So, and that's a new kind of challenge on the system. And, I think we've started to see that in some of the data we're collecting from some of our sites. So system strength is kind of the ability to resist those disturbances. And the traditional disturbances are what we've talked about, big in-feed losses. So like losing the North Sea link or losing the French interconnector. Traditional faults like a 400 kV transmission line going to earth and the voltage collapses till the fault protection clears it. These are the kind of traditional faults that we've been worried about. And I think that we've got to worry about new kind of faults, and the system strength resists those kind of faults. And I think the synchronous machines bring that system strength. You can't reprogram a synchronous machine without a big hammer, whereas all the other control systems you can reprogram.
Okay. And then final question, do you have a contrarian view, something that you believe that the majority of the market doesn't?
So most of what I do is contrarian. I think you go nuclear, biomass, wherever you want to go, connection skew. But I think given we're talking about stability today, then I thought about this. I thought I'd like to talk about reaction to faults and what codes and system operators seem to want plant to do. So in the old days, when you were connected to the grid, as soon as there was a fault, it was like trip off, because we don't want you on. We'll sort the grid out and then we'll bring you back on. That was all right when you had a little bit of distributed generation. I remember doing some projects in Crete and going into the control room and saying, what settings do you want us to trip off on? And they went, no, if there's some problem on the grid, you need to stay on. We're relying on you, wind turbines, to keep going. So that was like the first, that's a completely different attitude. And then we had, fault ride through. You need to be able to ride through faults. We don't want you to trip off. So, okay, that was it. And then we want you to provide fault current. So we want you to contribute fault current into the fault. And that's kind of then get ramped up on, and we're now on fault current on steroids. So when I talk about 9th of August 2019 and Hornsea disconnecting from the grid, it was trying to push reactive power from an offshore wind farm through a long AC power system to shore through the grid to respond to a transmission fault quite remote. So the transmission fault happens, there's a small voltage dip that appears on the system. By the time it gets out to Hornsea, it's relatively small. It reacts, pushes out a lot of reactive power into the grid to prop up the voltage. The fault clears. Suddenly all this reactive current's flowing and the fault's gone. And the voltage goes up. So the wind farm goes, the volt's gone up, quick, reverse all the reactive power. So it's trying to do this in a remote offshore wind farm. Don't make it do that. Just let it produce megawatts. Get your synchronous compensators, maybe batteries, other stuff that's located close to the fault to do that fault ride through stuff. Don't try and make everything look like an old synchronous machine which did all this stuff. Let's divvy up the services into stuff that does it best. Batteries doing frequency response, synchronous compensators giving system strength, offshore wind farms delivering megawatts. Let's try not to make everybody do everything, because that'll result in a massive cock-up at some stage.
Agreed. Guy, thank you very much for coming on Transmission. It's been a superb episode. We've covered so much ground. We'll definitely put some links into the show notes in terms of synchronous compensators, Statcoms, etc., so people can kind of swat up on that should they choose to. Thank you very much for coming on.
Thank you, Ed. It's been really interesting. Great interview technique. Thank you.
Thank you for listening to Transmission, a Modo Energy podcast. Transmission delivers conversations from industry leaders and experts exploring energy markets and the operations and technologies related to grid-scale battery energy storage. Check out our other episodes by searching Transmission wherever you get your podcasts. Check out the Energy Academy, our video crash course on how markets in Great Britain and ERCOT work, or head to modoenergy.com to see our written research. Thanks for listening.